Hi, everybody. We're continuing in on 6.3, part 2, and we're going to a topic called composition of linear transformations. Now, you've learned about composition of functions, a function of a function, composite functions, and we're, we're doing composite linear transformations. And so this is something this idea of composition of functions we've seen before. And we're actually going to relate it to, it's in the same it's in the same section with matrices for linear transformations. We're actually going to connect the two concepts. But first, let's just say what we're talking about here. So a composite function is, very simple. I have a function, I have T1, which goes from Rn to Rm. I have T2, which is a function from Rm to Rp. And now my function T is a composition of those two functions. So we're going to show that the composite function of two linear transformations is also going to be a linear transformation in its own right. We're going to show that. And we're also going to show that the matrix for the linear transformation of the composite function is actually going to be, ready for this, drum roll please, the product of the matrices of the, for T1 and the matrix for T2. But let's just state that more formally. So here we go. Theorem 6.11. So if T1 goes from Rn to Rm and T2 goes from Rm to Rp, and they're both, these guys, T1 and T2 are both linear transformations, and they have their standard matrices A1 and A2 respectively. So the composition function T from Rn all the way straight to Rp, which is defined by T of V is equal to T2 of T1 of V. And this is now T of V actually lives in Rp. V lives in Rn, T1 of V lives in Rm, like Mike, and T2 of T1 of V lives in Rp. That's, and anyway, this composition isn't a linear transformation. That's the first part of the theorem. And secondly, the standard matrix for the composite function T is actually going to be the product of the two previous standard of A2 times A1. It's going to be the product of these two guys. Okay, let's prove it. Let's get to some proving here. So first we want to show that T is a linear transformation in its own right. Well, let's just show that it has the properties. T of U plus V, that's T2 of T1 of U plus V, which is T2 of T1U plus T1V, which again, by the linearity of T2 is T1 of T2 of T1 of U, which is capital T of U, and T2 of T1 of U, which is capital T of V. So we've just shown that T of U plus V is equal to T of U plus T of V. So the composition has that property. Now let's do scalar multiplication. It's the same thing. T of CV is T1 of T2 of T1 of CV. You can bring out the constant, now bring out the constant again, and now you have C times T2 of T1, which is by definition of T, capital T, regular plain T of V. So yes, it worked. Now, that was easy, and the next part is also going to be easy. Oops, went too far. Because T of V, that's T2 of T1 of V, but T1 of V, as we've, is equal to A1 times V, because A1 is the standard matrix. T2 of A1 of V is A2 times A1 of times V. And now we know that matrix multiplication is associative. And so A2 times A1 times V is A2 times A1, parentheses, times V. But that means that A2 times A1 is the standard matrix because T of V is equal to this product times V. So we've just shown that this product of the matrices is the standard matrix for the composite linear transformation. And that is very, very awesome, which also is going to make it easier for us to find the the standard matrix for a composite function. In fact, let's do an example of it right now. So here's an example 3. T1 and T2 are transformations from R3 to R3. T1 of XYZ is 2x plus y, comma 0, comma x plus z. T2 of XYZ is x minus y, comma z, comma y. So it's whatever, messing things around. So we want to find actually two different compositions. We want to find T2 of T1, and we want to find T1 of T2. All of these are functions or transformations from R3 to R3. Well, A1, we can copy from this information here. A1 is this matrix. And from this information here, A2 is this matrix. I could, again, this we showed previously how to you can just look at the, you just sort of look at it and get the matrices right away. For those of you who don't remember how to look at it, 2x plus y, so that's 2x, 1y, and 0 z's. That's why I have 2, 1, 0. 0, well, that's no x, no y, no z. And x plus z is 1x, 0 y's, and 1 z, so it's 1, 0, 1. And same business over here. That's how we do it. So A is A2 times A1, and so A is A2 times A1, which if I multiply these two matrices out, that's the product I get, and that's the standard matrix for which one? Is it for T or for T prime? Well, if I do A1 first is the same. A1 first over here is the same as doing the T1 first, which means this is for T. Now for T prime, we're going to multiply the other direction, A2 times A1, and we get this matrix here, and that's the matrix for T prime. So it all works out beautiful. Now another advantage of using matrix, using this representing linear transformations in terms of matrices, is that it makes it easy for us to find an inverse, the inverse linear transformation, if there is an inverse. Not every function has an inverse. As you know, it has to be 1, 1, and on 2. So here's the definition. T1 goes from Rn to Rn, and T2 goes from Rn to Rn, and they're linear transformations. So if T2 of T1 of V is equal to V, and T1 of T2 of V is equal to V, then T1 and T2, then these two functions are inverses, and we say that they're invertible, or whichever way you want to say it. So that's the definition of inverse linear transformation, just like any other, which is basically kind of the same as the definition of inverse for any function. Now, not every linear transformation has an inverse. If the transformation is inverted, if T1, if it is, but if it does have an inverse, then it's unique, and we could just say T1 inverse. We could use there's one inverse if there is an inverse. One thing you do see here, by the way, is that well, actually, I'll let it play out. You'll see in a minute. And inverses mean like they always means, meaning if T of 1, 4, negative 5 is 2, 3, 1, that means T inverse of 2, 3, 1 is 1, 4, negative 5. So that's basically, inverse. It's like any other inverse function. Now here comes the big theorem. Drumroll, please. If T is a linear transformation from Rn to Rn with a standard matrix A, then the following conditions are equivalent. T is invertible, T is an isomorphism, and A is invertible. So basically, the matrix itself has to be invertible, and for the function to the transformation to be invertible, and the transformation has to be an isomorphism, which makes sense also because it has to be 1, 1, and onto. So all these, there are many conditions. These are cool, awesome. But if T is invertible, then the standard matrix is just going to be A inverse, which makes a lot of sense. So how do you find the inverse of a linear? So here's a linear transformation. How do you find the inverse? Well, turn this sucker into a matrix. So the top row is going to be 2, 3, 1. The next row is going to be 3, 3, 1. Next row is going to be 2, 4, 1. Right there. And now we just figure out the inverse the way we figured way back in chapter 2. And we get A inverse is going to be this guy right here. So T is invertible because the matrix has an inverse, and that is the inverse. And that is very awesome, very cool, and very awesome. I just want to mention one last thing before we move on. You can use the standard matrix for the inverse. Using the standard matrix for the inverse, you can find, now that we have the matrix, we could find the rule for T1. In other words, we started with writing T in this format, and then we changed it to a matrix format. But once we have the matrix, I could also move it back to this format, and easily enough. And the way you do that, well, one way to do that is what we're about to show you. One way to do that is to actually do a matrix multiplication. Take A inverse, multiply it by a random vector x1, x2, x3. This is what you get, this guy right here. That means the first component is negative x1 plus x2 right there. The next component is negative x1 plus x3 right there. And the next component is 6, negative 2, negative 3. But by the way, I could have done this just by, again, once you get used to it, you can just say, okay, that's my top row, 1, negative 1, 0. So this is going to be negative x1 plus x2 with no x3s. And that's negative 1, 0, 1. So that's going to be negative x1, no x2s, and 1 x3. So just like we said, you can go from here to there just by kind of looking at it. Same thing, we can go from here to there just by kind of looking at it. And then the bottom row is 6, 2, 6, negative 2, negative 3. So here it's 6, minus 2, minus 3. So it's all kind of, like I say, it's the kind of thing we just sort of, when you get used to it, it's very, very, very simple. Okay, that concludes the part 2. That concludes this video, and hope you enjoyed it and learned a lot. And we've connected the matrices for linear transformation with the composition of linear transformations. Very cool, very awesome, and we will see you next time. Ciao.